Why do we put the extra plate? Again, it's very simple. Because the maximum bending moment is at the what? At the bottom portion, right? Maximum bending moment is at the bottom portion. So if the maximum bending moment is the bottom portion, right? So we need to put some extra protection at the bottom part. That is why these cover plates are used to put the extra protection. Extra protection, right? Hello everyone, welcome to my channel Civil Maverick. In this video, I will show you the theoretical as well as practical demonstration of a built-up girder. First, I will explain the theoretical aspect of the built-up girder. Then I will take you to the side and show you the practical demonstration of the built-up girder. To get more updates about civil engineering information, please subscribe my channel Civil Maverick. Thank you. So before we understand the concept of plate girder, we need to know some important points, important concepts. If you understand this concept, then we can easily can have the knowledge of plate girder. So first, the point is that these are some important points I've written here. When the applied load is not very high, roll steel beams are used. Now, what is roll steel beam? See the definition here. Roll steel beams are created by taking a single piece of steel and subjecting it to a series of rolling operations in a steel mill, right? That means in a steel mill, through some rolling operations, we can create this. This is a roll steel beam you can see here, right? This is created from a single beam, single piece of beam, through some rolling operations in a steel mill, right? And see the maximum depth available in the market is Indian standard wide flange beam 600. Now what is 600? This is 600. You can see this depth, right? This is a depth, right? This is like this, okay? That means this depth is how much maximum available in the market? 600, right? This is called what? This is called top flange, and this is called bottom flange. Bottom flange, and this portion, this vertical portion is called web, right? So we are web, right? So maximum depth available is what? How much? 600 mm, right? That means when the applied load is not very high, then we can use this roll steel beam. I mean, this can be used in case of what? In your home building, right? Where the load is not that very high, or some other structures where the load are not very high. You can use this roll steel beam. Now the second point. See the point here. When the applied load is too high, that means the load is greater than this roll steel beam. The applied load is right, and the roll steel section is insufficient to carry the desired load. That means this section is not sufficient because load is very high now. Then built up beam is used. What is built up beam? What we do is that additional plates at top and bottom flanges of the rolled steel section beam are connected through riveting, bolting and welding, right? That means this is the rolled steel beam, right? Above this flange section we'll put some extra plate, or below this flange, bottom flange, we'll put some extra plate. Then this is what? A built up beam. See the diagram here. And this can be done through what? Riveting, bolting and welding. See the diagram here. This is a, see this is what? A roll steel beam, right? This is roll steel beam. Now this roll steel beam is not sufficient to carry the desired load because the load is a bit higher. Then what do? We'll put this extra plate here. Extra plate. This extra plate you can see here. We'll put here. And this can be done through what? Welding, riveting. Here riveting or bolting is done. See the bolt here, rivet or bolt. Here welding is there. You can see here welding. You can connect these plates to any method, welding, riveting or bolting. Now this is the beam, right? The beam will go like this. This is the beam, right? The load will apply on here. Now here it can carry a higher load than what? The roll steel beam. Now see the third point. Now we are coming to the plate girder concept. When the applied load is too high for the built up beam to sustain, then built up girder or plate girder is used. Now the applied load is very high, right? That high that this built up beam cannot withstand that applied load. Then we have to go for what? Plate girder, built up girder or plate girder. Now see here, when a word girder comes, remember that girder is for heavy loading. Heavy. See, girder and beams are same. If you say beam, see, all girders are beam, but all beams are not girder. It means what? Girders are nothing but beam, but beams are not. All beams are not girder, because this word girder is used for the word heavy. When a load is very high, very heavy, right? Then we have to go for what? Girder. Okay, we cannot go for beam then. We cannot use built up beam. We have to go for what? Girder. The shape of the girder is as same as beam only, but this will take or withstand very heavy loading. Remember that the word girder is for only heavy loading, right? Now look at this here, plate girder. Let me now show you the definition of plate girder. A plate girder is a structural beam that is commonly used in construction and engineering to support heavy loads over a span. The heavy word has to be there in case of plate girder or built up girder. It consists of two horizontal flanges, typically made of steel or other structural materials, a vertical wave connecting the flanges, and stiffeners to resist the of the buckling of the wave. Right. So this is a girder. You can see this is a girder, right? Plate girder. So it consists of what? See what are the components of a plate girder? Two horizontal flanges. Two horizontal flanges. See, this is the flange, right? Top flange, and this is also flange, bottom flange. Vertical wave. This is the wave, vertical wave, connecting the what? Flanges. This is connected to welding only, welding, right? To welding, this wave is connected with these two flanges. And stiffener. See, this is the stiffeners. This vertical stiffener, this is horizontal stiffener, right? These stiffeners are used what? To prevent the buckling of the wave, because the wave buckles. Because see, this wave has got a very less thickness, very few thickness. You can say only 12 mm, right? Very less. So, if there is heavy compressive loading, very high shear stress, then buckling might occur, right? To prevent this buckling, we have to use these what? Stiffeners, right? Now I explain one by one, but this is a basic concept. And why this is called plate? Because these all are plate. This is a single piece of plate. This is a single piece of plate. This wave is a plate. These stiffeners are plate, right? So these plates are connected through welding with each other, right? That is why it is called plate girder. Now let me tell you one thing. How can you differentiate between plate girder or built up girder and beam? See here, see the depth here, only 600 mm maximum that is available in the market. This you can find to steel table, right? IS code steel table, all are written here. Now this maximum is how much? 600 mm that is available in the market. But you know, like for example, in my bridge where I'm working, where I am like supervising a bridge, right? On built up girder bridge, this depth is, you know how much? That is 1400 mm. See the difference? 1400 mm. Like roll steel section only 600 mm maximum, and this is 1400 mm. It can be more than this also, but in my bridge I'm taking the example. There is 1400 mm. That means you can understand that it can carry a very heavy amount of loading, right? Because you cannot create a roll steel beam, roll steel section of this much of depth in the mill, in the plant, right? It's not possible, right? So we have to create part by part. That is what is called plate girder. All these are plates only, plates. I think the basic concept is clear to all of you, I guess, right? See, this is a drawing you can see here. This is a picture. Here, these are some plate girder, right? You can see here in a bridge flyover. This is a plate girder. This is the wave. These are the flanges. These are the stiffeners, right? These are the stiffeners, vertical stiffeners. So there are vertical stiffeners. There are horizontal stiffeners. So I explain when we have to go for horizontal stiffener also. Then I explain one by one. But this is the basic concept of plate girder. Why we have to go for plate girder? That you need to understand that, because plate girders can take very heavy amount of loading, and a maximum loading that is available, maximum size that is available in the market is only 600 mm ISWB, right? Now we will understand the component of plate girder one by one, right? So the first component that we have is the wave plate, then the flange plate, flange cover plate, stiffeners, wave splice, and flange splice. Now, what is the purpose of this wave plate? Waves are used to mainly resist the shear force, and flanges are used to resist the bending moment. So, if I draw the girder, right? So, this is the girder, and this is the wave. This is the wave plate, wave plate, and this is what the top flange plate, and this is what the bottom flange plate. Right. Now, what is the purpose of this wave plate? To mainly resist the shear force. So, or the shear stress. So, if I draw the shear stress diagram, so this is the shear stress diagram of a I section. That is the shear stress. You can see maximum shear stress is at the center, and there is a sudden increase in shear stress at the junction, right? This is junction. There is a sudden increase in shear stress just at the junction, right? But the maximum shear stress is at the center. So what does it define? What does it mean? It means that the wave, this portion is taking the maximum shear stress, right? The purpose of this wave plate is to resist the shear force. Now, what is the purpose of this flange plate? To resist the bending moment or the bending stress. Why? If I draw the bending moment, so bending stress, see, this is the bending stress, right? So clearly you can see this is tension, right? Simply supported beam, and this is compression. So maximum bending stress is at the bottom here, and this is at the top. So which part is taking the maximum bending stress? The flange plate, right? That is why they have written flanges are used to resist bending moment. I think that is clear to all of you. One, then we have the flange cover plate. Here, what do we do is that we put some extra plate. Why do we put the extra plate? Again, it's very simple. Because the maximum bending moment is at the what? At the bottom portion, right? Maximum bending moment is at the bottom portion. So if the maximum bending moment is the bottom portion, right? So we need to put some extra protection at the bottom part. That is why these cover plates are used to put the extra protection. Extra protection, right? Then we have the stiffeners. Stiffeners. So what is the purpose of the stiffeners? Let me show you. These are stiffeners. See, this is a vertical stiffener. This vertical stiffener is also called what? Transverse stiffener. Transverse stiffener. And this is a horizontal stiffener. This is called longitudinal stiffener. Longitudinal stiffener. Okay. Now, what is the purpose of providing these stiffeners? Stiffeners are used to make the wave safe from buckling, right? See, why we put stiffeners? I mean, see, the thickness of this wave plate is very thin, See, if you see the depth of this wave and the flange plate, it is almost 1500 mm. That is 1.5 meter almost. But you see the thickness of this plate. This is almost 1400 mm. This depth in my bridge actually mm. This thickness, this thickness is very less. How much? Only 12 mm. See here, only 12 mm. So thin. That means what? That means what does it mean? It means that this wave plate might get buckled because of the shear stress and the compressive stress. Because buckling takes place mainly due to compression and due to shear. Okay, so this wave plate might get buckled because of the shear stress and this compressive stress. To provide protection against buckling, right? What do? We have to put stiffeners. These are some extra plates, these stiffeners, so that this wave plate doesn't get buckled, right? That is the main purpose. Now, at what distance we provide, what should be the thickness of the stiffeners, and what is the condition that we provide this longitudinal stiffener, that we'll discuss one by one now. But this is the main concept. Why do you have to provide the stiffeners? Okay, and we have the wave splice and flange splice, right? The wave splices are the wave splices plates are used to connect two waves. See here, this is the wave, right? This is the wave. I mean, if I look at the length of the bridge, this is almost how much? 25,000 mm. That is 25 meter. And you don't get a wave plate of this much length. You cannot transport also. It's not possible. So what do we have to do? We assemble these plates, right, at the side with the help of this wave splicing, right? Suppose this is the plate and this is one plate, this is one plate, and we connect these two plates by this additional plate, this one. This is called the splicing. So we have to provide splicing plates for wave and the splicing plates for flange also, right? Bottom and top flange. I think the concept is clear to all of you, right? Now, see, this is a diagram here. Let me show you. This I have taken from the book Duggal, S.K. Duggal, Design of Steel Structure. Now, see here. This is a girder. This is the girder, right? This is the girder. This is the main girder. Okay, this blue line I have shown here. That is the main girder, right? Now, what is there? First, this is the cover plate. This is the flange cover plate. See this extra plate here. This one is the cover plate. Extra. Above this plate, we provide this cover plate. Similarly, at the bottom also there will be a cover plate, right? This one is a cover plate, right, at the bottom. Then what do we have? We have, see, this is the wave plate, this is the flange plate, and this is the bottom flange plate, right? Then we have the stiffeners. So you can see here, this is a stiffener. You can see this one is a stiffener. This is a vertical stiffener, and this one is a horizontal stiffener. Okay, see here, vertical stiffener, horizontal stiffener. And this is what wave splice. See, this is a plate. This plate is connecting this wave and this wave, because you don't have that much of length, right? So you have to connect these two plates by wave splicing. These are nothing but plates, right? So bolt and one plate, we connect two plates actually, both opposite side, both side, we connect the wave. Okay, I mean the concept is clear to all of you, I guess. Right, now if I discuss about the type of stiffeners, so there are two types of stiffeners. One is the transverse vertical stiffener, I have already discussed, and one I have the longitudinal horizontal stiffener, right? So this is the vertical stiffener or transverse, and this one is the longitudinal horizontal stiffener. Again, transverse vertical stiffener are of three types: end bearing stiffener, intermediate bearing stiffener, and intermediate transverse stiffener. Fine, we have three types of stiffener. One is end bearing, one is intermediate bearing, and one is the intermediate transverse stiffener. Three type of vertical stiffener. vertical or transverse stiffener. Okay, one by one, let us discuss. The first one is end bearing stiffener. End bearing stiffeners are provided to transfer the load from beam to the support. At the end, certain portion of weight of beam act as a compression member, and there is possibility of crushing of weight. To prevent it, end bearing stiffeners are provided. Okay, so if I see, this is a support, suppose here is a support and here is support, right? So at the end, this is the end portion, right? This is, I can say, end. This is A, I say, this is B, end A, and this is end B, right? So at the end, both the end, right, and and B, at the support portion, this wave act as a like compression member. So here, what might happen? This wave might crush due to excessive compressive force. So we have to protect this wave, right? So to protect this wave, we have to put stiffeners at the ends. That is why it is called end bearing stiffener. So we'll provide some stiffener here at the end. Here also we'll provide the stiffener at the end. This is called what? End bearing stiffeners. Because this crushing gets due to compression only, right? So I'll show you, I'll take you to the site and show you on my side. At the side also I have provided this end bearing stiffener. I'll show you that. Then you can clearly understand that. Okay. Now the second is the intermediate bearing stiffener. Why do we have to provide this intermediate bearing stiffener? If concentrated point loads are acting in some portion of the beam, local buckling of wave may occur. To prevent this, intermediate bearing stiffeners provided. So if some point load is there, suppose on this beam some point load is there, okay, anywhere, if there is a point load, then only you have to provide what? Intermediate bearing stiffener to resist the local buckling, because local buckling might occur because of this point load. To prevent that, we have to provide what? Intermediate bearing stiffener. Okay. And third one is what? Intermediate transverse stiffener. What is the use of this? To resist the average shear stress, the thickness of wave is quite less. Use of thin waves may result into buckling due to shear. Hence, intermediate transverse stiffeners are used to prevent shear buckling of the wave. So, I have told you already, this is the shear stress diagram, right? So here, this wave might get buckled due to shear, excessive shear stress. We have to check. If this wave is safe against the shear, then we don't have to provide the intermediate transverse shear. If this wave is not safe against shear, that is, that clauses are given in the IS code, I'll show you. Then we have to provide what? Intermediate transverse stiffener to protect against buckling due to shear, right? Right. This is the concept of transverse stiffener. Now we have to understand why do we have to provide the longitudinal or horizontal stiffener. Where do we have to provide longitudinal horizontal stiffener? Now, to increase the buckling strength of the wave against compression along the longitudinal direction, longitudinal horizontal stiffeners are provided. Now, if you see again this diagram, see, this is the shear stress and this is what? The bending stress. So along this longitudinal direction, that means this vertical is the transverse direction, right? Transverse. And along this, right, this is what? The longitudinal direction. So what is happening here? See, above this neutral axis, this is neutral axis, right? This is compression and this is what? Tension, right? So here, this, I have told you, this is very thin, only 12 mm, right? Very thin. The whole wave has a depth of 1400 mm, very high depth. Now this wave can gets buckled due to shear and due to compression also, because the column always gets buckled due to compression, right? So we have to provide protection against this buckling due to this compression, right? I have already told you the vertical stiffener. These vertical stiffeners are provided against the shear stress, right? And to provide protection of this wave against its compression, right? These horizontal stiffness are provided along the what? Longitudinal direction, because this is what? The longitudinal direction, right? That is the main concept. Now we'll see at what condition we have to provide this transverse and horizontal stiffener, right? So there are some codal provisions, IS 800 2007. So let us discuss one by one. First one is the self weight of the girder is the self weight of the girder. Suppose this is the girder, right? This girder has got a self weight, that is how much? Capital W by 200. Small w is the self weight of the girder. Factor self weight, right? So how much is the self weight of the girder? Total factor load on the girder, the load acting on the girder, like the dead load and the live load, okay, divided by 200. That is what the code is given. And second one is what? The economical depth of the girder. So what should be the depth, so that we can get economical design? That is, D is how much? Mk by Fy to the power 1 by 3. What is M? M is the bending moment. K is what? D by Tw. D is what? The depth of the wave. We see here, depth of the wave is D. Tw is the thickness of the wave. This is the Tw, thickness of the wave. Fy is the yield stress of the wave. Okay. This is the point number 3, very, very important. If K is how much? D by Tw. If D by Tw is less than or equal to 67 epsilon, no intermediate transverse stiffener is required. Only N bearing stiffener is provided. Okay. If this is less than 67 epsilon, no intermediate transverse stiffener is required. Only N. See, N bearing you have to provide always, N bearing at the end, right? Because at the end, the load is transferred to the support, right? At that time, the wave acts as a compression member. So you have to always provide this N bearing stiffener. But whether you will provide the intermediate transverse stiffener or not, that will decide based on some parameter. The first one is, if this is D by Tw, D means what? Depth of the wave. Tw is what? The thickness of the wave is less than or equal to 67 E, then you don't have to provide the transverse stiffener. Point number 4. If K value is between 67 epsilon and 200 epsilon, it may be possible to have the girder without intermediate transverse stiffener. Here also, you can have the girder without any intermediate transverse stiffener if this condition exists also. But designer has to check for shear buckling. Now that is given in page number 59 and 60, IS 800 2007. Okay, if you check this page number 50 and 60 in this IS code, then you will find the guidelines to check the shear buckling effect, right? So if the girder is safe against shear buckling, we can have the girder without intermediate transverse stiffener in spite of having this value. See, what does this value mean? K value. If K value is more, what does it mean? What does it mean? K means what? D by Tw. So if the K value is very high, what does it mean? That the depth is very high compared to the thickness. Thickness is low, depth is very high. That means what? The wave is very thin. That means the wave is what? Very, very vulnerable to what? Buckling due to shear and compression, right? So if we get more value of this K, it means that the wave is vulnerable to buckling. Okay. Now, if the value of K is greater than equal to 200 epsilon and less than equal to 250 epsilon, both transverse and that's vertical and longitudinal horizontal stiffness are provided. Okay. See, if you get this value, you don't have to provide any transverse stiffener, only N bearing. If this is the value, you have to check whether the wave is safe against shear buckling or not. That you have to check. If it is not safe against shear buckling, then you have to provide the intermediate transverse stiffener. And if the value is this, you have to provide both transverse vertical, that means transverse means intermediate transverse, and the longitudinal stiffener also. Longitudinal means this is a horizontal stiffener, where at distance of 0.2 d from the compression flange. That means from here 0.2 d, this is the value of d. At this distance you have to provide the horizontal stiffener also. This is provided against the compression effect, right? And if the value is k is what, more than 250 and less than 400, second layer of longitudinal horizontal stiffener is provided at the location of neutral axis. So this is the neutral axis. At here also you have to provide the second layer of longitudinal stiffener. Normally, if k is equal to 100 to 110, then the girder can be designed without intermediate stiffeners to reduce the fabrication cost. Obviously, if you have intermediate stiffeners, then more material will be there, the cost will be high. Normally, if the K value is this, you can have a girder without any intermediate transverse stiffener. But again, I am telling you to check against the shear buckling, and that is given in page number 50 and 60 of IS 800 2007. This is a codal provision. And point number 8, thickness of transverse bearing stiffener is designed in such a way that the outstand from the wave is not more than 20 TQ epsilon, where TQ is the size of the thickness of the bearing stiffener. So this is a top view of the girder. This is the wave plate. If you see from the top, you will see what this wave. You will see the wave. Okay, and this is what, this is the transverse vertical stiffener. This one. If you see from the top, you will see this transverse vertical intermediate transverse stiffener. You will see. And what should be the outstand? Outstand means what? From the wave, how much should be the distance here? In my bridge, that is 150 mm is provided. So how do you decide this 150? This is the outstand. How do you decide? That should be what? 20 TQ into epsilon, where TQ is the size of the thickness. Okay. This is the codal provision, and there is some span to depth ratio. If D by L is 1 by 15 to 1 by 25, this is for in building. If this is 1 by 12 to 1 by 18, this is for highway bridges, and 1 by 10 to 1 by 15 is for girder in railway bridges. And for additional codal provision, you have to go to page 63 to 68 of IS 800 2007, right? And this is my bridge that I am supervising. There are 3 girders. Okay, this is one outer girder, this is one outer girder, and this is the central girder. So here I have 2 what cross girder at the end. This is N cross girder, this is N cross girder, and this is almost 25-meter bridge. 25 meter. Okay, and you can see this is what splice, flange splice, because this is one plate, this is one plate, this is one plate. These 2 plates are connected by this splice. These 2 plates are connected by this splice, right? This is the flange splice. Similarly, you will have the what waist splice also. You can see here in the diagram. Say this is the depth 1400 mm. This is the girder, right? This is the girder. You can see this plate. These are bolting. These are what? This is a splicing plate. This top and bottom are what? Splicing plate. 2 plates you have to provide to connect the flange, right? Top and bottom. This is what? This is a wave splice. You can see wave splice. Wave splice. This is the wave. This is going along this direction up to how much? 25 meter. And you have to provide splice plate. Both side. Okay, both side you have to provide. And these are the bolt that through which you connect. I will take you to the site and show you this splice plate also, right? So see the thickness very thin, 12 mm only, and the depth 1400 mm, very high depth. Okay, fine. So I hope the concept is clear to all of you. Then I will take you to site now and I explain the part there one by one. If you have understood the theoretical part, then you can clearly understand the practical part also. Thank you. So let's go to the site and understand the practical part. Thank you.